Okay. Okay, so the general idea is that the positive linear combinations, okay, positive linear combinations of columns of A, okay, should span the entire space. Okay, should span all of the space, which in this case is three-dimensional space, R3. Okay. All right. I think you probably get the intuitive idea. Okay. Let's try to state this a little bit more formally because we're now dealing with just planar, okay, planar grasps. But eventually, when we consider spatial grasps, three-dimensional objects in the three-dimensional space, okay, we're going to need a more precise statement of this. Okay, so let's try to do that. Okay, so let's state the above more precisely. Okay, so first thing we're going to do is we're going to define something called the convex hull. Okay, so first thing. So let's say that we have some vectors, A1, A2, okay. Let's say we have n of them. Okay, and these are, we're trying to be general now, so let's say these are m-dimensional vectors. Okay, so we have n of these m-dimensional vectors. Okay, we're going to say that the convex hull, okay, the convex hull, okay, and this is the definition of convex hull, okay, of these vectors, okay, is the set, okay, so it's the set of vectors formed by taking linear combinations of the A's in a special way. 1 to n of Wi times Ai. Okay. Now these weights are scalar. Okay. So each of these weights have to be non-negative, greater than or equal to 0. Okay, and the sum of the weights, okay, they have to sum to 1. Okay, so that's the convex hull. So given a collection of vectors or points in Rm, its convex hull is defined by this set. Okay, you know, if you're seeing something like this for the first time, it might seem like something rather messy. In fact, it's not. Let me just show you with a few examples. Okay, so let's look at in R2. Okay, so here's the plane. Let's draw some vectors. So here's A1, here's A2, here's A3. Okay, so the convex hull of A1, A2, A3 is just, these are points. Okay? It's that triangle. Okay? So this is the convex hull. Okay? Now if we have more points, this time I'm not going to draw the vectors. Let me just represent them as points. If we have 4 points like this, convex hull is going to be this quadrilateral. Okay. If we have 1, 2, 3, 4, these 5 points, its convex hull is going to be all right. So what do we do here? Okay. We have a tendency to want to draw a nice polygon, so we might want to do this, but that's not correct. That's the convex hull. Okay? Okay, so that's the convex hull of those 5 points. Okay, so we have notion of a convex hull. All right, so now we can state the our form closure result a little more precisely. Okay, so let's now consider the equation AX equals B. Okay, where A is a matrix of the form of dimension, or rather of size n by m. Sorry, so it's m by n, I believe. M by n. Okay. And B is m-dimensional, and X is n-dimensional. Okay. So think of the columns of A as these vectors AI. Okay, so we can say that a solution x greater than or equal to 0, okay, exists for all arbitrary B. Okay. Okay. So this means if and only if, necessary and sufficient condition. Okay. Okay, this is true. If and only if an open ball in, so let's see, X is n-dimensional. An open ball in Rn. Okay. Okay, so, open ball in Rn centered at the origin. Okay, so this open ball has to be in the interior, okay, lies in the interior, okay, of what? Of the convex hull. Convex hull of what? Convex hull of the columns of A. Of columns of A. Okay?
What's the meaning of open ball?
Open ball is exactly that. It's just it's a ball. Okay, it's in this case it's an n-dimensional ball. Okay, and it's open. So closed ball, open ball. Okay, so actually, well, to be a little bit precise, we have to say there exists. Let's add a there exists at the front. Okay, so there exists an open ball in Rn centered at the origin. Okay, so let's fix the grammar a little bit here. That lies in the interior of the convex hull formed by the columns of A. Okay? All right. So if we look at this case here, let's go back to the original problem. So we had in three-dimensional space, you still have this drawing in your notes, I hope. Okay, we had some various, I guess, points like that. Okay, so some tetrahedron. Okay. Okay, so what you have to do is you have to draw an open ball here, so a three-dimensional ball here. And you have to ask yourself, is there some three-dimensional ball centered at the origin that lies in the interior of the convex hull of these 4 points, in the interior of the tetrahedron here? Okay? If you can find such an open ball, then yes, a solution exists. So yes, we have form closure. Okay? Okay, now suppose, okay, let's now look at the case where the L's, L1, L2, L3, okay, are all 0. Are all 0. Now what happens to these points is that they now all lie on the xy plane. Okay. They form a square or diamond. Okay, so that's what happens. Okay. Okay, so now let's apply a result. So does there exist an open ball, okay, in R3? So does there exist a three-dimensional open ball? So the key here, three-dimensional. Centered at the origin that lies in the interior of the convex hull of these 4 points. Okay? So you see that because it's a three-dimensional ball, okay, and the convex hull is a square in the xy plane, there's no way that this ball can be in the interior. Okay? This top part and the bottom part are sticking out. Okay? Okay. So this fails our test. Okay? So physically, all right, so mathematically everything I think is consistent. Physically, what's going on? Why is this a problem? Okay, so what's wrong with this? Okay, so this corresponds to this. Okay, so what's wrong with this? Looks okay. What's wrong with this? Well, if we look at the equations, ax equals b again, what we have are, now if I can remember, 0, minus 1, minus 1, 0, 0, 1, 1, 0. Okay, I believe it's going to look like that, x1, x2, x3, x4. Okay, and over here we have b1, b2, b3. But now let's remember what the b1, b2, b3 were. That's just the, okay, it's the external force, the negative of the external force in the x direction. Okay, negative of the external force in the y direction, negative of the external moment, z component. Okay, so it's that. Okay. So now if you look at the last row, okay, because the last row is all 0, okay, there's no way to resist an external moment. Okay, so if these are 4 fingers, and I'm holding this object this way, and somebody comes and applies a moment, okay, I can't resist it instantaneously. Okay. So if these pins, if you nail the pins in, we all make little errors, right? So if the pin is not firmly up against this object, if there's a little bit of a tolerance, it's going to wiggle quite a bit, and very easily it's going to slip out. Okay, so that's why. So that's what's going on physically. Okay, we're unable to resist external moments with this configuration. Okay. All right. Okay, let's go. Let's get back. So let's see, where were we? All right, so now let's think about this a little bit. Okay. Okay, so for planar grasps, how many fingers do we need? Minimum number of fingers do we need? Okay. So assume that we have no friction. Okay. We live in a planar world. We're only grabbing planar objects. We need, so according to this condition, right, we need, okay, the convex hull, okay, to be at least 3-dimensional. Okay. So that means we need at least 4 points in space. So that means we need at least 4 fingers. Okay. So a minimum, okay, of 4 frictionless point contacts. Okay, are required. Okay, at least 4. So if you're going to build a robot hand that's picking up planar objects, okay, and you're worried about friction, that you're not going to have enough friction, it's good to have 4 fingers. Okay. Okay. So the next question is, what about 3-dimensional objects? Okay. So for spatial grasps, okay, of 3D objects, how many fingers do we need? So if we're going to construct a hand with no friction at the fingertips, how many fingers do we need? Okay, somebody said 7. It's an awful lot. I only have 5. Somebody said 7. Any others? Higher, lower? Taking bids? Okay, so either this means everybody agrees that it's 7, or you don't have opinion. You don't have an opinion about this.
5.
Okay, we have a 5 here. 4, okay. 6? 6, no. Okay, so we have a range of numbers, 4, 5, no 6, strangely enough, 7. Let's answer this question, okay? So we can do this, actually. So here's a 3D object. Let's have these contacts here, various contacts, okay? Frictionless, so the forces can only be applied in the normal direction. Okay, so here's F1, F2, F3, F4, F5. Okay, we don't know how many we need, so let's call this F sub n. Okay, so here are our forces. Okay. Let's draw a reference frame in the middle. There's our reference frame. Okay, next thing, what do? Write down the equations for static equilibrium. Okay, so static equilibrium. Okay, sum of the forces equals 0, sum of the moments equals 0. Okay, so sum of the forces. Okay, from 1 through n, and including the external force. Okay, this equals 0. How many equations? 3 equations. Okay, sum of the moments, Ri cross Fi, I from 1 through n, plus external moment. Okay, so this time the moments are 3-dimensional, okay, because now we're working in 3-dimensional space. Okay, this has to equal 0, so 3 equations. Okay, all right, so static equilibrium equations, we have 6 equations total. Okay, and the forces look like what? Okay, so each force is going to have a direction. Okay, let's call that direction n sub I, n hat sub I. So it's a unit vector. Okay, indicating the direction that force Fi is applied in. And then the magnitude is x sub I. Okay, so I from 1 through n. Okay. So now if we write the static equilibrium equations with the force in this form, then we get the following set of equations. We have n hat 1 up to n hat n, R1 cross n1, Rn cross n hat n. Okay, this times x1, x2 up to xn. Okay, so this has to equal, okay, arbitrary external force and arbitrary external moment. Okay, so this is our Ax equals b in the 3-dimensional case. Okay, so we have 6 equations. Okay, 3-dimensional, 3-dimensional, 3 plus 3, 6. Okay, so this, our matrix A in this case, is 6 by n. Okay. All right, so the condition for a solution to exist is, for a positive or non-negative solution x to exist, is what? That a 6-dimensional open ball centered at the origin must be in the interior of the convex hull of these columns of A. All right, so let's draw a picture to help us. Okay, so now, okay, you have to use your imagination. This is now six-dimensional space. Six-dimensional space. It's like a yin-yang sign. Okay, we have a six-dimensional open ball here. Okay. And we now have to construct the convex hull of the columns of A. Okay, so convex hull, I don't know, looks, I don't know, some, whatever. You get the idea, right? Convex hull. Okay, so we have 1, 2, 3, 4, 5, 6, up to n points. Okay, how many points do we need? To create a six-dimensional volume here, we need, okay, so in 2 dimensions, to create a 2-dimensional area, we need how many points? 1, 2, 3 points. In 3 dimensions, if we want to create a volume, we need at least 4 points. Okay, so you see the pattern? We need 1 more point. So we need, in 6 dimensions, we need 7 points. Okay. All right, so we have the answer. So whoever said 7, I'm not going to give you a prize or anything, but yeah, 7. We need 7 fingers. Okay, so now you see why friction is a good thing. Okay, otherwise, if we had no friction on our hands, we would all be walking around with 7 fingers. Okay. Need a minimum of 7 frictionless point contacts. Okay, so thank God for friction. Okay, you don't have to write this if you don't want to. Okay, so friction is a good thing.